Hey, welcome. Ever stop and wonder how computers actually do all the incredible things they do? Today, we're going to pull back that curtain. We're going to dive into the fundamental mindset behind it all, a way of thinking that can take a seemingly impossible problem and make it totally solvable. So, let's get into it and learn how to think like a computer scientist.
I mean, really think about that for a moment. You type something into a search bar, or you ask your phone for directions, and poof, the answer is just there. It's instant. How in the world is that even possible when you're dealing with just a mind-boggling amount of information?
Well, the secret, it's the algorithm. And that's not just a fancy word for a set of instructions. It's so much more. It's like a perfectly crafted recipe, a really clever strategy for cracking a problem. And learning to think in algorithms, that's the core skill we're talking about today.
Okay, so before we can even begin to talk about making something fast, we have to tackle an even bigger question. How do we know our solution is even correct? Because in the world of computers, mostly works can be an absolute disaster. We need a way to guarantee our solutions are right every single time.
This is where the whole idea of a proof comes in. A proof isn't a guess. It's not an opinion. It's a rock-solid, step-by-step, logical argument. You start with things that are undeniably true, we call those axioms, and you use pure logic to build a case for a conclusion that just can't be argued with.
And this is so important. We're not just talking about theory here. Think about the software that runs our banking systems or medical equipment or even spacecraft. You can't just cross your fingers and hope for the best. Proofs give us that certainty, that guarantee that an algorithm will do exactly what it's supposed to.
All right, check. We have a solution that's correct. We've actually proven it works. But, that's really only half the battle. Now we have to ask, is it any good? And in the world of computer science, good almost always translates to fast.
So what does fast even mean? It's a tricky word, right? It's not about whether my new laptop is faster than your old one. We need a universal way to measure this stuff. The real question is, when the problem gets bigger and bigger, how much more work does our algorithm have to do? Does the effort grow a little bit, or does it just explode?
This table says it all. Let's say n is just the number of things we're working with. Look at those two columns. When n is tiny, like 10, the difference isn't a big deal. But just watch what happens when n jumps to 10,000. The inefficient n squared approach completely blows up to 100 million operations. Meanwhile, the efficient one, it's barely breaking a sweat at 130,000. That's the difference between instant and, well, maybe you should go make a coffee. Or 10.
And here is where things get really cool. That n log n you just saw, that's not just a pretty good score. It's been mathematically proven to be a hard speed limit. For any algorithm that sorts by comparing items, you fundamentally cannot do any better than this as the problem gets bigger. It's like a law of physics for computation. Knowing these limits is what this is all about.
Now, an algorithm doesn't just exist in a vacuum. It's only as good as the data it has to work with. How we choose to organize or structure all that information can make or break our solution.
Take a look at this. This is called a binary search tree, and we're watching it add the number 13. Notice the rule is dead simple. If the number is smaller, you go left. If it's bigger, you go right. That's it. It's such a simple idea, but it has these huge, powerful consequences.
So why bother with a structure like this? Well, because that simple left-right rule means you can find things, add things, or get rid of things incredibly fast. Way faster than if you just had everything dumped in one giant list. Every decision you make cuts the number of things you still have to look at in half.
And the binary search tree is just one tool in the toolbox. There are tons of others, like hash tables. Just imagine a magical function that takes any piece of data and tells you exactly which bin to put it in. That's the basic idea, and it allows for lightning-fast lookups. It's actually the secret sauce behind a lot of modern databases.
Okay, so we've got our data organized nicely. Now what? How do we actually build the algorithm itself? Well, it turns out we don't have to reinvent the wheel every single time. There are common strategies, kind of like design blueprints, that we can use over and over.
Yeah, we're not starting from scratch. These big ideas with names like greedy algorithms or dynamic programming give us a framework, a solid starting point for attacking whole classes of problems.
Let's look at a greedy algorithm. The strategy is exactly what it sounds like. At every single step, you just make the choice that seems best right now. So, for making change, perfect. You just keep grabbing the biggest coin you can without going over. It's simple, it's intuitive, and in this case, it actually works perfectly.
But here's the million-dollar question.
What if the best choice for right now isn't the best choice in the long run? What if taking the obvious step now actually traps you later on? The greedy approach is fast, but it's not always right, and that's exactly why we need other blueprints in our toolbox. All right, so we've covered proving things are correct, measuring their speed, and even some strategies for building them. But the final, and maybe the most fascinating piece of this puzzle is understanding the limits. Are there some problems that are just too hard for any computer to solve efficiently?
And the answer is a resounding yes. Not all problems are created equal. Some problems have these elegant, super fast solutions, and others, well, others seem impossibly hard. So computer science actually organizes all these problems into categories called complexity classes.
Okay, the most famous distinction is between P and NP. Think of it like this. P problems are the ones where we can find a solution fast. Sorting a list is a great example. NP problems are the ones where if somebody just gives you an answer, you can check if it's right really fast. Finding the absolute shortest route to visit 100 different cities is a monster of a problem. But if I give you a route, you can check the total distance pretty easily.
And this all leads to the biggest mystery in the field. Seriously, there's a $1 million prize for anyone who solves it. The question is, are P and NP the same thing? In other words, if you can check an answer quickly, does that automatically mean you can find it quickly too? If the answer is yes, it would change everything. Problems we think are impossible today could suddenly become solvable. And right now, nobody knows.
So, thinking like a computer scientist is all about this journey. It's about starting with a foundation of certainty, analyzing for speed, choosing the right tools for the job, and finally, understanding the limits of what's even possible. And as our computers get more and more powerful, the real question for all of us is, what are the next great challenges, right on that edge of possibility, that we should try to solve?